Okay, Matt Roscoe here at the University of Montana with a second lecture for our chapter on Wilson's theorem in our number theory class, Math 326. Okay, so where are we at? We've talked a little bit about Wilson's theorem and talked a bit about how the converse of the theorem is not very useful, but it is true. And then we did a quick example. So where we're at right now is this fifth bullet. Let's go ahead and go to that page, extension of Wilson's theorem to quadratics. So it turns out that Wilson's theorem allows us to get a little bit of a handle on how quadratic equations, or at least one particular class of quadratics, can be solved. And it's this one. It says the quadratic congruence x squared plus 1 is congruent to 0 mod p, where p is an odd prime, has a solution if and only if p is congruent to 1 mod 4. So that's a pretty surprising place to start our study of quadratics. What it seems to indicate is that some quadratics in modular arithmetic have solutions and others do not. So, I mean, just thinking about this a little bit, p congruent to 1 mod 4, so this would be numbers like 5, right? 5 is 4 times 1 plus 1. So it leaves remainder of 1 when divided by 4. So the congruence x squared plus 1 congruent to 0 mod 5 would have a solution. But if I went just 2 more beyond 5 to 7, then we would say, which is congruent to 3 mod 4, we would say that the congruence x squared plus 1 congruent to 0 mod 7 has no solution. So right away you're encountering kind of new structures, things that we're not used to. You know, usually quadratics in the reals, most of them have solutions either in the reals or the complex numbers. So that's kind of interesting to think about. We found some sort of a limiting factor, at least in a very simple quadratic congruence setting. So let's see if we can prove this, and then we'll take a look at an example problem and use it to find some quadratic congruence solutions. Okay, so I'm switch over to my Elmo cam here, and let's start by writing the number. Let's see, writing the hypothesis down. X squared plus 1 congruent to 0 mod p for p an odd prime has a solution if and only if p congruent to 1 mod 4. Okay, let's go ahead and see if we can get a handle on the proof. Let's go ahead and identify a solution. Let's let A be an element of the least residue set 1, 2, 3, all the way up to p minus 1. I guess we don't include 0 here because, of course, 0 wouldn't make any sense. 0 plus 1 would be 1, and 1 could never be congruent to 0. So let's let A be a solution to the equation in question, x squared plus 1 congruent to 0 mod p. So let's see, since p doesn't divide a, or a doesn't divide p, we can state that a to the p minus 1 is congruent to 1 mod p, right? This is Fermat's little theorem, right? So right away we can say that, you know, even though this we're picking one of these and saying it's a solution, but this is also true. I should say, and since A solves x squared plus 1 congruent to 0 mod p, we get this solution, or this, I guess, we said a squared plus 1 would be congruent to 0 mod p. And it turns out that these two, the combination of these two results, is what gets us the forward direction in the proof. Let's see how this works. if a squared is congruent to 0, if I just simply add -1 to both sides, I'd get a squared congruent to -1 mod p. And so now the idea is to somehow inject this result into this result and squeeze out that result. Okay. So here's how it works. We take the first congruence. So I'll just say combining, we get that 1 is congruent to a to the p minus 1. But I'd like to put some 2's, some squares in there. So what I'll do is I'll say that this is the same thing as a squared. But if I factor 2 out of this even number, then I've got to divide that even number by 2. So it'll be p minus 1 over 2. Convince yourself of this fact. This is the hardest congruence to see. What we're doing is we're literally saying, well, this even number, p minus 1, because p is an odd prime, I can write it as 2 times something, right? And the 2 I factor out, it would be 2 times p minus 1 over 2. Okay, so now I can use this result right here to replace a squared with -1 to the p minus 1 over 2. So hopefully you can see that what's going on is this replacement is here, and I guess this equality starts with Fermat. I guess congruence equality. Okay, so you should be looking to see, or just that 1 has to be, oh, I guess this would be mod p. So we can see that 1 is congruent to -1 to the p minus 1 over 2 mod p. So equating, I guess, first and last, right? And that's where we can now start thinking about what p has to be in order for this to be true. You can see that this number, right, this exponent right here on -1 would have to be even. The whole thing would have to be even in order for this to be true. So thus p minus 1 divided by 2 must be an even number. Okay, so far so good. Okay, so if p minus 2 must be an even number, let's just think about p. By the division algorithm, p, an odd prime, must be of form either 4k plus 1 or 4k plus 3. Of course, if it was 4k, then it would be an even number. If it's 4k plus 2, it would also be even. So there are only 2 forms that it could take, 4k plus 1 and 4k plus 3. We look at each case. So p minus 1 over 2 for each case. So let's take a look at case number 1. P minus 1 divided by 2. If p was 4k plus 1, we'd have 4k plus 1 minus 1 divided by 2, which would just be 4k divided by 2, which would just be 2k. And so that makes sense because what we said is that this number must be even. And what if p minus 1 divided by 2, if the p was of form 4k plus 3 minus 1 divided by 2, we would get 4k plus 2 divided by 2, which would be 2k plus 1. So we see that if p is equal to 4k plus 3, the second case right here, that p minus 1 divided by 2 is odd, which is impossible. So P must be of form 4k plus 1 for a solution to exist. All right, so that's the forward direction in the proof. Let's go ahead and adopt, or I guess take a look at the reverse direction. So for the converse, remember we have to do the reverse direction because this is an if and only if, right? This is not only a necessary but a sufficient condition, right? So for the converse, consider the product p minus 1 factorial, and this is where Wilson's comes in. You notice, like, so far nothing has happened here that smells like Wilson's, right? So look at this product, p minus 1 factorial. So let's just think about it for a second. It's p minus 1 factorial is going to be, I'm going to write it from low to high. Start with 1. 1 times 2 times 3 times 4 times all the way up to p minus 1. But I'm going to actually be a little bit more careful about it because of the way I want to group it. I just realized. So I'm going to say that, notice that this is p minus 1 is even, right? So that means that someplace along here I'm going to get to the middle, right, of the string of digits that make up the p minus 1 factorial. And that middle turns out to be p minus 1 over 2, times p plus 1 over 2. That's the very middle, right? So you kind of think of this as like the middle of the set. And then up to the last two, I guess, p minus 2 times p minus 1. Okay, hopefully you understand what that means. This is p minus 1 factorial. We've got the product from 1 up to p minus 1, where these are the two middle terms that split the even number, right, of numbers being multiplied. Now, thinking about how this works in a modular sense, I'm going to move this down here. So in a modular sense, we can leave this as 1 times 2 times 3 all the way up to p minus 1 over 2. But what we could do is we could report this one as a negative number and these ones as negative numbers or negative modular equivalent. And the way we do that is we just subtract p from them. So I think it's easy to see that this one over here, right? So I'll just leave this little line in here, leave this one unknown, and go up here and call this one would be negative 2, right? And this one would be negative 1. So again, p minus 1 is congruent to negative 1, p minus 2 is congruent to negative 2. Convince yourself of that fact by just subtracting p from this one, subtracting p from this one. But then this one's a little harder, but it's if you think about it a bit, if you subtract p from this one, you're at p plus 1 over 2. You'll end up at negative p minus 1 over 2. Okay? So what we see is that there's sort of this this symmetry, right, that goes on here, left and right, when we think of it this way, which means that really all I'm doing is I'm squaring each term and then keeping track of how many negatives I have. So I could think of it like 1 squared times 2 squared times 3 squared times ... all the way up to this one, p minus 1 over 2 squared. But then I have to think about how many negative ones there are, right? And you can see there are exactly the same number of negative ones as there are pairs, and the number of pairs are, is this number right here, right? Because this number counts how many there are up to the middle I guess, the line of that separates, I guess, the first half and the second half. So it turns out that the right exponent to put on -1 is p minus 1 over 2. Okay, so slick little way of rewriting. All right. Looks like that's the end of my book. I'll get a new one out. Okay. So we could continue sort of rewriting this and saying that, instead of, having the square on each term, I could pull the square out of everything and say this is really the same as 1 times 2 times 3 times all the way up to p minus 1 over 2. So that whole thing, right, being squared, all times the 1 to the p minus 1 over 2, which, if you kind of look at it closely, this is just a factorial. It's sort of the first half, of the run from 1 to p minus 1 being squared. So a way to say this would just be to say that this is p minus 1 over 2 quantity factorial, right? But that whole thing is being squared. Again, times the -1. Oh, I missed the negative here, right? That should be a -1 to the p minus 1 over 2. Okay. Okay, so now choosing p to be equal to 4k plus 1, in other words, letting this p be 4k plus 1, and invoking Wilson's theorem, we get this. So again, if p is equal to 4k plus 1, then we know that this thing is even, and so this becomes basically -1 to an even number, right? And so it's just 1. So we end up with this thing. But what Wilson's theorem says, again, keep in mind that this is all equal to p minus 1 factorial, right? And Wilson's theorem says that p minus 1 factorial is congruent to -1 mod p, right? So I guess to just review, we chose this to be 4k plus 1. That makes this into a 1, which just brings this down. We know from before that this is equal to p minus 1 factorial. And we know from Wilson's, right, that this is congruent to -1. And so this is the end. It shows, what it shows is that p minus 1 over 2 quantity factorial is a solution to x squared plus 1 congruent to 0 mod p when p is chosen to be 4k plus 1 as desired. This might not be immediately apparent to you, but convince yourself this is a number squared congruent to -1, right? So if I added 1 to both sides, it would be a number squared plus 1 congruent to 0. And that's exactly what we're trying to solve right here. So bravo, there it is. One thing, important aside, and that is that when p is equal to 4k plus 1, the solution to x squared plus 1 congruent to 0 mod p is just this number right here, right? P minus 1 over 2 factorial. And I guess you probably want to do it mod P, right? So this is one thing that's not included in the statement of the theorem, but basically is constructed in its proof, and that is that this is the number that's a solution. And if it's a solution, can you think of what the other one will be? Every quadratic we kind of usually think of as having two solutions. If we think of this as a positive number, then we could just take its negative value and it would also be a solution, right? Because we're squaring and the negative would go away. So is negative p minus 1 over 2 factorial mod p. I hope that makes sense, right? And it's kind of one of the places where quadratics seem to be somewhat similar to, in the reals. There should be two numbers, a positive and a negative root here. And yeah, so let's see if we can apply this then to some sort of a practical end here. And then end, let's see. So here's the final example. Consider the two quadratic congruences. X squared congruent to 1, negative mod 19, and x squared congruent to negative 1 mod 17. Predict which will have a solution, then find it. I should say find all solutions. Let's go ahead and do that next. Well, I mean, we know that these things only work when p is of the form 4k plus 1. So here, 19 is equal to 4 times, let's see, 4, 16, yeah, 4 times 4 plus 3. So this is not equal to 4k plus 1, so no solution. I hope that makes sense, right? We know that this number right here has to be of the form 4k plus 1. Let's check 17 is going to be 4 times 4 plus 1, which is a 4k plus 1, so solutions exist. Okay, and the solution, we're told, basically by the theorem, right, that the solution is of the form, so I'll just say this one, right? Solutions are p minus 1 over 2 factorial and negative p minus 1 over 2 factorial. So let's just find the first one. P minus 1 over 2 factorial would be the same thing as 17 minus 1 over 2 factorial. So let's see, that's 18 divided by 2, 9 factorial, right? Oh wait, what am I doing? 16 divided by 2, 8 factorial. Right? Good thing I looked at my notes there. That's the same thing as 8 times 7 times 6 times 5 times 4 times 3 times 2. Don't need to include the 1. And then we could just do some arithmetic. You could multiply this all out and reduce it if you wanted to, but I think it's easier to sort of think about, I don't know, see if we can get close. Like 17 is the modular setting, so if we could get an 18, we'd be in good shape, right? So that means the 6 and the 3 would make an 18. So that's just a 1, right? So 6 and 3 would just be a 1. Let's see, what else could we do? The 5 and 4, those guys would be a 20, which is just a 3. So I could cross those off as a 3. Let's see, the 8 and the 2, those are 16, which is just a negative 1, right? So we could cross those guys off and call it a negative 1. So we'd have 7 times 3 times negative 1. So this would be negative 21. Let's see, adding 17 to that is negative 4. Adding 17 again to that would be, so this is negative 4, which is adding 17 again would be 13. This is all mod 17. So 13 mod 17 is one of the solutions, and then the negative of that would be, so I would say that solutions are 13 mod 17 and negative 13 mod 17, which is just 4 mod 17. And of course you should probably check it. I mean, this is the first time we've done one of these. So what we're checking is to see is 13 squared, I guess we're trying to see if it's congruent to negative 1. So 13 squared plus 1, is that congruent to 0 mod 17, question mark? Well, 13 squared plus 1 is the same thing as 169 plus 1, which is the same thing as 170 plus 170, not plus 1, which is, of course, congruent to 0 mod 17. And let's see, 4 was the other one. 4 squared plus 1 congruent to 0 mod 17, question mark. So let's take a look. 4 squared plus 1 is the same thing as 16 plus 1. Well, that's 17, which is of course 0. So indeed, our method has worked, and it's actually found our solutions for us. All right, well, that's really it for now. I've talked probably too long anyway. I hope that this gives you some good sense of what's in the chapter here. The big thing you should concentrate on, of course, is Wilson's theorem. I think that's the bigger, more useful theorem. But the interesting side note about quadratics is also, I guess, informative. It shows you how number theory builds upon itself and how Wilson's comes into play, as well as Fermat in this early, I guess, look at quadratic congruence. All right, wish you luck in your homework. I'll see you when I get back.